Alright, so in this video I'm going to try to keep it short. I'm going to give you an idea as to how we would define limits for functions of several variables. So it's a little bit different than what we did for one single variable, because now we have a little bit more, more variables to begin with, but we also have to consider the distance function that we're talking about. So we'll start with just writing the definition. So the definition says that we say that L is equal to the limit as x comma y goes to a point, let's say x naught, y naught, of the function of two variables f of x, y. And if you want to do 3 or 4, the definition will at that point be the same, basically. We say that limit L, or that limit is equal to L, if and only if for every epsilon, so this is going to mean for every epsilon greater than 0, there exists a delta greater than 0, such that the distance between x comma y and x naught comma y naught being, let's say, greater than 0 and less than delta implies that the distance between f of x, y, and this limit L, no, that's okay, and L is less than epsilon. All right, so that looks horrible. Let's try to break it out. Let's try to explain what it is. So let's draw a quick graph of some function on two variables, x, y, and we get the z value from it. So let's draw a quick graph there. Let's say that you have like a curve, like a bell. And something like that. All right, so the idea of the limit is that, let's say the function you are going to claim, let's grab more colors. We need all sorts of colors. That one, it almost disappears, but it's okay. We'll say that value in the z-coordinate is going to give us L for that point. And we are going to say that that's the limit of the function at the pair x naught comma y naught, if and only if for every epsilon greater than 0. So what are you going to do? You're going to look at your L, and you're going to look at L plus epsilon and L minus epsilon. So you're going to go and make kind of like not a band in this case. We had a band whenever we were talking about in one dimension, but now you're going to grab a ring around, or a whole two planes, L plus epsilon, L minus epsilon. So they're going to go in this direction as well. So you're going to have, it's kind of like a sandwich now. You're grabbing a sandwich of width 2 epsilon. So you're going to do that, and you're going to mark that around your L. And the goal now is to find some delta down here, that when I make a circle, this right here is the equation basically is telling you that the circle with entries x comma y centered at x naught y naught of radius delta, everything in the interior of that circle is what we're considering down here. So this equation here, the pairs x comma y, so what I'm trying to say is that the pairs, whatever that was, the pairs of point x comma y such that the distance between x comma y and x naught y naught is less than delta that right here is just a circle, or the interior of a circle of radius delta around this point x naught comma y naught. So this radius here would be delta. So now your goal is to find that delta, so that what? So that whenever you map everything up here, so you look at the function of all these guys, whatever it gives you up here is going to be within the distance between epsilon apart from this f function. And by the way, I did, that's why it looked weirdly to me. So because L is just a real number and this function is just a real number, so the distance function here is just the absolute value, the difference of the absolute value. That's why I'm drawing a kind of like a pancake thing, or like a sandwich, because I'm just going in the vertical direction. I'm going up by some epsilon up and epsilon down. So now that then tells me that if the image of every element in this circle gets mapped to something that is within epsilon apart of L, and I can do that for any epsilon, then I know that the function is getting arbitrary. I can get the function arbitrarily close to this value L as I get arbitrarily close to the point x naught, y naught from any direction. So that's what makes the limits in several variables more subtle. Because now, whenever we were talking about limits in one single variable, well, you simply had a point A. You could approach it from the left or from the right, and that was it. But from here, you have infinitely many directions you can approach the point from. You can approach from this line. They don't even have to be symmetric. You can approach from any direction, and it doesn't matter from what direction you approach, you should get the same value. So that's why these limits in 2 dimensions become a little bit more complicated. So the idea is now we have to define the limits in terms of distance functions, and the way you do it is in this way. You grab any epsilon, you make that epsilon sandwich, I'm going to call it. So you want all the images to be within epsilon apart of L, and then you have to be able to find a circle of radius delta around the point x naught, y naught, that the whole circle, the whole interior of the circle gets mapped within epsilon apart of this L. So say that you grab epsilon to be 0.000001, well, there should be a delta that can get you within that distance of the limit. Now remember though, this right here tells you that the function needs not to be defined at x naught, y naught. So you don't have to have the function being defined, but you have to get arbitrarily close to it. Now, what I just mentioned about approaching from different directions does tell you a way that you can actually prove that a limit doesn't exist. If you choose 2 different directions to approach a point and you get different values, that automatically tells you that the limit does not exist. So let me go ahead and write the definition of continuity and explain basically where it comes from, and we're going to wrap this video up right here. All right, so now continuity. So we say that f is continuous at, let's do that, x naught, y naught, if and only if, let's do 2f's for if and only if, 3 things happen, and you know these 3. 1, the limit should exist. If the limit doesn't exist, well, you can stop the conversation there. There's no reason. Something funny is happening there. So you're going to say that this exists. Now, the limit can exist and the function not be defined at that point, so you're going to require that the function be defined at that point. So you're going to say that x naught, y naught exists as well. And it's all fun and games if those 2 exist, but they are not equal to each other, so they better be equal to each other. So we're going to say that both the limit as x, y goes to the pair x naught, y naught, if then it gives you the same value as the function. All right, so this video will be very theoretical. We're going to leave this one there. And now in the next video, we'll solve problems. So thank you for watching, and I'll see you in the next one.